Howdy gang, welcome back. Today we are reviewing for exam 3. So remember, your exam 3, the exam on logarithms and exponentials, is this week, this Thursday. If you're taking the test online with me, of course, you'll do the same thing that we've always done. You'll sign into the Zoom link, but you'll do it from your phone. Set up the phone so I can see your desk, your hands, your paper, all that good stuff. And then I'll give you the thumbs up to go ahead and launch HonorLock on your computer and start the test. If you would prefer to take the test at the testing center, that's fine. I'm going to make a blanket reservation for the whole class. You can just walk in there anytime, building in Northwest Campus, 2nd floor, anytime after 12:30, and you can get started on the test then, as soon as they're ready for you. Soraya asked, are we having class Tuesday? I assume you mean next Tuesday? Yes, we are. So next week is Thanksgiving, right? And the college is closed on Thursday and Friday, but we do indeed have class on Tuesday, the 23rd. Exam 2, I think I've graded the exam 2s. Let me take a look. So depending on when you took the test, like if you took a makeup or something, I might not have graded your exam 2 yet, and I apologize for that, but the majority of exam 2s are graded. Oh no, I see your class. Yeah, there's actually quite a few of you whose exam 2s have not been graded. Let me see. Yeah. Oh, I see what happened. I graded the makeup cohort, but I haven't graded the main cohort. All right. I'm sorry about that. I thought I had these done weeks ago. So yeah, I'll bang those out real soon. I'll bang those out like tonight if I can. Sorry about that, Jill. Thank you. Yeah, no, don't hesitate to rush me. You can definitely poke me. It is the case that I have a lot going on, and from time to time I make mistakes. Things slip my mind. This is definitely one of those. I totally forgot to do that for you. So yeah, those of you still waiting on your exam 2 grades, I'm so sorry, and they'll be in as soon as I possibly can. I do see that one person has submitted the transformation Jello's worksheet. A reminder, everybody does need to do that, and that will earn you some bonus points on your exam 2. So please go ahead and download and complete that transformation worksheet. It's just 4 short problems, and those are stats that I really need for the class. So please do that as soon as you can. All right, but today we're reviewing for exam 3. There are a few problems and problem types that I want to look at specifically, and then I'm happy to spend the rest of the class time doing whatever you guys would like to do. So please let me know in the chat what you would like to see. Let me close this out so we're not showing everybody's grades, and we can get to it. Can I do the test on, maybe I could ask you for a little bit of clarification there. Can you do the worksheet on paper?
Worksheet, yeah.
I would really prefer that you print them out, because these are things that the department has to share with each other. I have to give these to my colleagues, and we all look at them together to decide how to score them. So it's really nice to have that uniformity, to have the consistency, because they're going to be passed around to like 10 or 15 other faculty, and just out of kindness to them, it would be really nice if we could print the worksheet. If you're having trouble finding a place to print, you can print on campus. That is an option. I think it's like 10 cents a page, something like that. So if you can find a dime sitting somewhere, you can print at the library. If you're having trouble with it, I could always like print a few copies and leave them with my secretary in Unit 2 also. Let's go ahead and start doing the thing. This is MAC1140, section 009, which is a pre-calc class, and today is the 16th of November, 2021. Today we are reviewing for exam 3. And just to get started here, I'm going to remind you the sections that are on the test. It's basically just chapter 4. 4.1 on exponential functions. This is where we introduced the concept of an exponential function. We talked about their graphs, their domains, their ranges, and we looked at transformations of those graphs, shifting them up, down, left, right, flipping them over, stretching them out, all that stuff. Section 4.2 is on the number e. And the natural exponential function this is basically just a repeat of section 4.1, but focusing on the function e to the x and its translates and transformations. Then we had section 4.3, which was on logarithm functions. So things like the graph of a logarithm, the domain, the range, transformations of those graphs, just the basics, basically the same as 4.1, but with log functions instead of exponentials. Then there was section 4.4, which was on laws. This was like expanding logarithms, combining logarithms, using those three fundamental properties of the log function to rewrite log statements. And then there was section 4.5 on exponential and logarithmic equations. And that's where we left off last week. We talked about exponential equations in class, and then I posted this video lecture because last Thursday was a holiday. I posted this video lecture talking about logarithmic equations. And what I want to do today, I want to kind of summarize this section and solve a few of each of those exponential and logarithmic equations for you today, that for sure. Before I do that, let me annotate this list just a little bit. So this was like graphs, domain, range, transformations, same thing in 4.3, graphs, domain, range, transformations. And here there's a big one too, also evaluating. Right, so like evaluating the base 2 log of 1/4, that sort of stuff, using the definition to see if you can evaluate a logarithm without a calculator. Those things, I just want to remind you, there was quite a bit of graphing in each of these sections. And then in 4.3, in addition to the graphing, there was a good number of problems, probably 10 or so problems in that homework set that just had you either rewriting log statements as exponential statements or evaluating log statements using the definition of the logarithm. So like I said, the first thing that I wanted to do here today, after giving you this list, of course, is recapping section 4.5. So exponential equations, these are equations where the variable is in an exponent. And the way we solved these, you would try to isolate the exponential term with the variables. Then you would take a logarithm and use those properties of logarithms to move the variables down out of the exponent. And that would give you a simpler equation, an equation where the variables are no longer in the exponent, which you would then solve. So sort of the magic step here is taking logarithms. This was like our new operation, take logs. It's like squaring both sides or taking square roots on both sides. It's a new operation that you can perform to an equation to get a new equation whose solution is the same as the original. And then the magic is, because of the properties of the logarithm, those variables can come down in front, and no longer do you have an exponential equation. You may have a linear or quadratic equation, something like that. Logarithmic equations, very similar. Instead of being equations where your variable is stuck in an exponent, these are equations where your variable is stuck in a log. And the procedure to solve these is super duper similar. First, you want to combine and or isolate the logarithm term. With the variable, right? If there's log terms that don't have your variable in it, you don't need to isolate those, but you definitely need to isolate the ones with the variable. And then, just like to solve an exponential equation, you take logarithms because logarithms undo exponentials. To solve a logarithm equation, you need to undo the logarithm. And the operation for that is to exponentiate. And you always do this using the base of the given log, of the given logarithm. So if your logarithm equation has like your variable stuck inside a base 2 log, you would exponentiate base 2. And then get rid of the logs, right? This gets rid of the logs. I'll show you some example. And after you've done that, you solve the resulting equation. There's one additional step. Check your answer. You might have multiple answers. The reason for this is that, remember, a logarithm equation is one where your variable is stuck inside a logarithm. The logarithm, any logarithm, has a kind of sensitive domain. You can only plug positive numbers into a logarithm. So if you get an answer in step 3 that makes the inside of the original logarithm negative, you need to throw that answer away. This never happens with exponential equations because if your variable is in an exponent, well, exponential functions, their domain is all real numbers. They never get upset at us. But logarithms, they can get upset at us. If you try to plug 0 into a log or -2 into a log, it will get upset. So there's this additional step for logarithm equations. You need to check your answers. And the other catch here, when you take logarithms in an exponential equation, you can use whatever base logarithm you want. I told you guys I will always use the natural log because that's my favorite. It's the nice one. When you're solving logarithm equations, you don't get to pick the base. You have to exponentiate using whatever the base is in the logarithm that's in the equation. So kind of a few subtle differences between these, but overall, very, very similar. And taking logs is the operation that undoes exponentials. Exponentiating is the operation that undoes logarithms. So the big goal here is to kind of isolate the problem term and then do whichever operation is necessary to get rid of the problem, either the exponential, which you get rid of by taking logs, or the logarithm, which you get rid of by exponentiating. We've seen a handful of these. If you watch the video lecture, you've seen a bunch of these. I want to run through just one or two of each. I'll do a simple one for each and a slightly more complicated one for each. And in order to keep things fresh, I'm not going to recycle examples. So the complicated examples here will be a little bit different than the ones we've seen in the other video. That is, if you haven't watched the video, you need to. So please, if you haven't, don't take this as a replacement for that. It is not. All right. First things first, let's solve a nice, simple exponential equation. how's about two plus e to the negative 5x equals 10. So this is an exponential equation because my variable is stuck up here in an exponent, right? E raised to something, that's an exponent. My variable stuck up there. So I follow that procedure for solving exponential equations. I want to get this term isolated. That is the exponential term. I want to get him alone, then take logs, simplify, solve the equation I get from that. So my first step is to isolate that exponential, meaning I need to subtract the 2 over. So I get e to the negative 5x equals 10 minus 2, which is 8. Now that I have my exponential all alone, I can take logs. That means we're going to put both sides of this equation inside a logarithm, and I get to choose the logarithm I use. I always like to use the natural logarithm. So my left-hand side becomes the natural logarithm of e to the negative 5x, and the right-hand side becomes the natural logarithm of 8. Now, the natural logarithm of e to the negative 5x is just negative 5x. Right, the ln of e to some stuff is always just that stuff. I'm not really doing anything, I'm just simplifying, so the right-hand side stays the natural log of 8. This is that resulting equation, right? And you notice that the original equation is exponential. This is linear now. This is easy to solve. To solve this, I just divide both sides by negative 5. So this would be x equals negative natural log of 8 over 5. And if I want to approximate this as a decimal, this stuff out, I can type negative natural log of 8, close that parentheses, divide by 5. I get negative 0.4159, say. Negative 0.4159, rounding up that 4th decimal place. This would be your exact answer, and this is an approximation rounded to 4 decimal places. I have a quick question for you. Is negative ln of 8 divided by 5 the same as negative ln of 8 divided by 5? Could I simplify like this?
No. No.
Yeah, hell no. But what if you're not sure? Or what if it's something else and you want to check? How could I check?
Plug it into a calculator and see if you get the same answer.
Yeah, very good. So I already know that the negative ln of 8 divided by 5, the first guy here, this is about 0.4159. I can calculate the other guy, negative ln of 8 over 5, then parenthesis close, and I get something else, right? This is negative 0.47. Even if I round to the 4th decimal place, that's 4700. And these are not the same number, right? Different numbers. So yeah, not the same thing. All important, these parentheses then, right? If you just wrote I know I harp on this a lot, matter. negative ln of 8 over 5, if I write it like this, you don't know which one I'm talking about, right? It could be the negative ln of 8/5, or it could be the negative ln of 8 all over 5. This is ambiguous. So make sure you write your parentheses very clearly. Tell me what's inside the log and what's outside the log. Okay, I'll ask more questions like this as we go through other exercises here today. Is there anything you guys would like to ask about this problem?
For me, it's very easy to see what you can do during this problem, but could you give us a difficult problem that it may not seem as easy at first?
Absolutely. Yeah, in fact, I have one in mind. So here's a curveball I haven't thrown you in any of the lectures so far. What if I have two exponential terms with different bases? Maybe something like this. The first thing I would notice here is that I cannot start by taking logs on both sides because the ln of 0 is undefined. And there's no nice way to simplify the ln of 5 to the x minus 4 to the x plus 1. So this guy's got some challenges built in, right? It's not immediately obvious what to do. Any ideas? No bad answers here.
Would you put the power in front of each?
After taking a logarithm, like if I just had the ln of 5 to the x, if I had ln of this, then I could pull the power down. But if I take the ln of this whole thing, then these are different bases and different powers, and there's this subtraction between them. So it's not the same as all this raised to the x. So before I can do anything that would help me get those powers down, right? Like taking logarithms will help me get powers down. Before I can do that, I need to do something else.
5 to the power of x equal to 4 to the power x minus 1, then put it to natural log, and then...
Yeah, very good, very good. So if I move this term over to the other side, then I can take logarithms on both sides, and each piece will be something that simplifies nicely. You guys see that? So while the ln of this is hard to work with, and worse, the ln of 0 is undefined, the ln of this and the ln of this are both very easy to work with. So kind of it's like that same step, right? Isolating the exponential. I've got an exponential term and just that alone on the left, and an exponential term and just that alone on the right. So this is a much friendlier version of the same equation. And I say friendlier because when we take logs, and again, you could use whatever base logarithm you want, but I will use the natural log because he's my friend. We get this, which is a very manageable expression. And it's at this stage where I can start bringing powers down. The thing to be careful of is that the x plus 1, right, 4 is being raised to the power of x plus 1. 4 is being raised to the whole power x plus 1. So this is like a chunk, this x plus 1 here, and he needs to be treated as a chunk when he comes down. So applying that property of logs, the left-hand side just becomes x times the natural log of 5. The right-hand side becomes parentheses x plus 1 times the natural log of 4. And those parentheses around the x plus 1 are things that I often see people miss or forget. So again, parentheses, they're really your friends. If there's one take-home lesson in pre-calculus, it's learn to use parentheses carefully and correctly. Okay, this is pretty good stuff. This is not a bad equation to solve. This is a linear equation. This natural log of 5, it's just a number. This natural log of 4, it's just a number, right? The ln of 5, let's take a look. Ln of 5, it's like 1.6. The ln of 4, a little smaller, like 1.3. So this is like 1.6x equals 1.3 times x plus 1. Not a hard equation to solve. So don't be intimidated by the notation. Remember, natural log of a constant is a constant. So how would we solve this equation? This is our resulting equation that we need to solve. Again, no bad answers. Just give me a guess.
Divide
Divide ln 5 by both sides.
Yeah, I think I heard divide come from both people. We could divide both sides by the natural log of 5. That's an option. I do think there's a better move, though. If I distribute this ln4 over these parentheses, kind of my goal is to get x alone, right? And dividing both sides by ln5 would get this x alone, but it would attach something more complicated to this x, right? Because this whole thing is being multiplied by ln4. If I divide by natural log of 5 here, then this piece is getting a little more complicated. So before I start dividing over, I'm going to distribute this ln4 across these parentheses. So we will divide eventually, but before that, let me make this suggestion. Because my long-term goal here is to take every term with an x and put it on one side, and every term without an x and put it on the other side. I want to be able to see exactly which terms have x's and which terms don't. So we expand everything. Now I've got 3 terms, this guy, and this guy. These two have x's. This one does not. So I'll leave this one over here and move this one to the left. That gives me x times ln5 minus x times ln4 equals ln4. And this is nice because now on the left-hand side, every term has an x in it. So I can factor the x out on the left, and then I'll divide over. And it just saves me a few steps. If you started by dividing by ln5, as long as you do everything very carefully, you will eventually get to the same answer. But this is just a little faster, a little more nicely organized. And I will continue this up here. Oop, I need to close paren here, don't I? There we go. So after pulling the powers down, I distribute everything, expand everything out, and then pull all the terms with an x to one side and all the terms that don't have an x to the other side. That allows me to factor an x out on the left. And now I have x times this constant is equal to some other constant. So now I can divide over, right? There are no more x's to deal with, just this one. Now I can divide over by this. And I get x equals the natural log of 4 divided by the natural log of 5 minus the natural log of 4. Let's go ahead and approximate this as a decimal just to get a feel. Again, careful with parens. Natural log of 4, close that paren, divided by, I've got 2 terms downstairs here, so I need to open up a parentheses because your calculator is just going to do division, multiplication straight up left to right, following the order of operations. So I want to divide ln4 by all of ln5 minus ln4. So ln4 divided by open paren, ln5 close minus ln4 close close. So this says take the natural log of 4 and divide it by the whole chunk, ln5 minus ln4. That's what I want. So that's about 6.213-ish. Now we've been rounding to 4 decimal places, so 6.2126. I have a question kind of in the same spirit as this one. Can I cancel ln4 here? Is this the same like ln4 over ln5 minus ln4 cancel? 1 over ln5 minus 1? Is that allowed?
No.
Yeah, again, no. Why not?
ln4 isn't a factor of ln5, so you can't factor it out.
Perfect.
So
That's
it's
exactly
multiplied,
how-
then yes.
Yeah, exactly how I would say it. So remember, you can only cancel common factors top to bottom. So if you're wondering, can I cancel this term? Ask yourself, well, can I factor it out of the top? And can I factor it out of the bottom? ln4 is a factor of the top. The top is ln4 times 1. But ln4 is not a factor of the bottom because this piece right here doesn't have a natural log of 4. So nope. And again, if we wanted to check, I already know that ln4 over ln5 minus ln4 is about 6.2126. I can compute 1 over 1 divided by parentheses ln5 close minus 1 close. And I get that's about 1.6409. Which is not 6.2126, right? Very different animals. So nope, can't do that, not kosher. And I love the way you said that, Suzanne. It's exactly correct. Cannot cancel it because ln4 is not a factor of the bottom. It's a term of the bottom. That's not the same as being a factor. That's exactly how I like to think about it too. I'll tell you things like this make really good true false questions on the test. So like, is this equal to this? Or is this equal to this? Fun questions. Okay, thoughts, questions on either of these? Okay. The other types of equations we've seen, right? These are exponential equations, both of them. Other types of equations we're trying to prepare ourselves for are logarithmic equations. Same thing, I'm gonna start with one that's kind of simple, and then we'll look at one or two that are maybe less simple. So how's about 2 plus the natural log of 3 plus x equals 7. I would say this is a simpler logarithmic equation. It is a logarithmic equation because my variable is here inside this logarithm. So we follow that procedure. First, we want to combine and or isolate the log terms. There's only one log term, so there's nothing to combine, but I do need to isolate it before I can get rid of it. So there's this 2 over here that's gumming up the works. So to isolate the log term there, I would subtract 2 from both sides. That would give me the ln of 3 plus x is equal to 7 minus 2, which is 5. And next is that magic step. To undo a log, we exponentiate it. What base should I use if I'm going to exponentiate to kill a natural log?
E.
E, yeah. Always use the base of that logarithm. And the natural log, remember, is the base E logarithm. So I'm just going to write exponentiate base E over here as a little reminder. Remember what exponentiate means? It means to put in the exponent of. So to exponentiate base E means to put in the exponent of E. And it's not the same as raising both sides to the E power. 5 raised to the E is 5 to the E. 5 exponentiated base E is E to the 5. Very different things. So we have this new word because it really is a new operation. The left-hand side, we have E raised to the ln of 3 plus x. So this is what I get when I exponentiate both sides here using the base E. The reason we do this is because of how this and this interact. E raised to the natural log of your mom is your mom. So E raised to the natural log of 3 plus x, it's just 3 plus x. I'm only simplifying, I'm not doing anything to the equation, so the right-hand side stays E to the 5. This is that resulting equation. After we exponentiate and clean up, we get this nice simple linear equation. And if I want to solve this, the only thing that's keeping x from being alone is the 3. So I'll subtract 3 from both sides. And remember, powers of E should always just be left as powers of E. I don't care if this is like 35.7215. Just leave it as E to the 5. So this is x equals E to the 5 minus 3. It is often the case that we want a decimal approximation because it's hard to say exactly how big this number is. I can approximate. I know E is a little smaller than 3, right? So it's like somewhere in the neighborhood of 3 to the 5. But if I want to see, on the TI-84, you'd type second and then divide to get the E. On the 83, sorry, you're on the 30 here. Where's our button? You would type second and then the ln. You see, and that says E to the x. So you type second ln, and that would give you the same thing. It would give you an E, and then you hit this button right here called a caret, the little up arrow. On the 83, it's right here, the little up arrow to get you into the exponent. And what we're trying to type is E to the 5. Oh, sorry. E to the 5, and then we need to get down out of the exponent. So we hit the over arrow to get down, and then minus 3. And 145.413. So this would be my exact answer. And this would be my decimal approximation. And there will be questions on the test where I require you to give the exact answer, either in terms of the number E or in terms of logarithms. There'll be questions where I ask for a decimal. There'll be questions where I ask for both. You need to be comfortable with both. Any questions on this guy? There's one thing we should be careful of here. There's a step I haven't done yet, and that's checking the answer. What I mean there is you need to verify or make certain that when you plug this number in for x, the inside of this logarithm remains positive. Now, yeah, 145 is big. When you add 3 to that, you get something big and positive, somewhere in the neighborhood of 148. And that is certainly positive. So I don't really need to worry here. The problems where you need to worry are problems where you end up combining logarithms before exponentiating, because that process has the ability to change the domain. Let me grab an example. I think this is one that we have not done in the video, or or elsewhere. So let's solve the log base 2 of x plus log base 2 of x minus 3 is equal to 2. Our first step here is to combine and isolate logarithms. I do have two logarithms here, and they both have variable stuff inside of them. So I need to combine these into a single logarithm before I can exponentiate. So my first step here is going to be to rewrite that left-hand side as a single base 2 log with the inside x times x minus 3. On the right-hand side stays 2. I'm using the log law. The rule is that the log base a of something plus the log base a of some other thing is equal to the log base a of their product. I could exponentiate in my next step, but before I do that, I just like to clean up the inside a little. So if I distribute x times x minus 3, that's x squared minus 3x. Right-hand side is still just 2. And now look at this equation. This is nice, right? I've got a log of some variable stuff equals a constant. This is a single isolated log term. So I am now at the step where I can exponentiate to get rid of the logarithm. So that's my next move. I'm going to exponentiate. What base should I use here?
2.
Good. Always using the base of the given logarithm. So the log that I'm working with is a base 2 log. In order to kill the base 2 log, I need to use the base 2 exponential. So that'll give me 2 to the log base 2 of x squared minus 3x equals 2 to the 2. Simplifying on the left-hand side, 2 raised to the base 2 log of some stuff is just that stuff. So this is just x squared minus 3x. And on the right-hand side, 2 to the 2 is 4. And this is a quadratic equation. And I know how to solve those. I'm going to pull the 4 over and factor. Worst case scenario here, we'd need the quadratic formula, but I think this time we'll get lucky. X squared minus 3x minus 4. That factors as x minus 4 times x plus 1. So I get x minus 4 times x plus 1 is equal to 0. Setting each of those factors to 0 on their own, this gives me x equals 4. This gives me x equals -1. And you wouldn't be crazy if you said, okay, I'm going to stop here, I'm done. But you would be making a mistake. What should I do from here?
X cannot be -1.
Yeah. So, and I want to be clear about this. It's not necessarily the issue that x is negative here. It's that when I plug this into the original expression, the inside of the logarithms become negative. So -1 is an issue because I would have the base 2 log of -1 here. That's undefined. And here I'd have the base 2 log of -4. So first, let's write this down. If I check x equals -1, I have the log base 2 of -1 plus the log base 2 of -1 minus 3 is -4 equals 2. And both this and this are undefined. Because you cannot take the log of a negative number. So I got to rule this guy out. I can also check x equals 4. There I get the base 2 log of 4 plus the base 2 log of 4 minus 3 is 1 equals 2. And this is fine, right? No problems here, no problems here. So this would be the answer.
If x were to be negative and you plug it in and there's no problems and it's like in the parentheses it's positive, then that would be valid. That would be one of the answers.
Yep, that would be just fine. And I'm glad you asked that because I had a similar question. What if after doing all this, I get x equals 1 as an answer? Would that be okay?
No.
No, right? I can
Yes.
plug 1 in here, but if I plug 1 in here, I get the natural log or the base 2 log of -2. All right, so this guy would be undefined at x equals 1. So exactly like you're thinking, like you're saying, it's not the positivity or negativity of x that is the problem. It's the positivity or negativity of the inside of the log that is the problem. So it's very possible that we have a problem where you get a negative answer for x, which is just fine. You just need to verify that when you plug it into the original equation, nothing is undefined. In other words, the inside of the logs are not negative. So good comment, good question. Any other thoughts or questions on this fellow? Okay. I haven't gotten any specific problem requests. So thinking about that list that we had here, these are the things that are on the test. Is there any particular thing that you guys would like to see from any of these sections? Anything that we're nervous about, like expanding or combining logs or finding domains of logs or transforming graphs of exponentials? Domains, okay. Yeah, I think it's good to kind of recap our domain stuff. Real quick. From earlier in the semester, we had 2 domain red flags. One of them was variables downstairs in a fraction. And there we needed to make sure that the bottom, the denominator, is not 0. So you figure out what values of x would make the bottom 0, and then you kick those out of the domain. We also had a rule that we're concerned about variables under even roots. Like if you have some variable quantity under a square root or a 4th root or a 6th root, there you needed to make sure that the inside was non-negative, greater than or equal to 0. The new domain red flag that came from studying logarithms is variables inside logarithms. And like we were just saying, you cannot take the logarithm of 0 or the logarithm of a negative number. So here you need to make sure that the inside is strictly greater than 0. And these rules you need to remember, not just for this class, but for calculus as well. So this third guy, this is the new one. And let's use these rules to find a domain. How about the natural log of 9 minus x squared divided by x squared minus 1? So there's two red flags here. What are my red flags?
The bottom cannot be negative. And what is within inside of ln 9 minus x squared cannot be negative or 0.
Yeah, so we need 9 minus x squared to be strictly greater than 0. And we need the bottom here, x squared minus 1, to not be equal to 0. So my red flags, two of them, right? I've got variables downstairs. So I need to make sure x squared minus 1 is not 0. And I've got variables inside a log. So I need to make sure that 9 minus x squared is strictly greater than 0. So I need to figure out what values of x would make x squared minus 1 equal to 0. Those have to be kicked out of the domain. And I need to figure out the solution to this inequality, because those are the only numbers that I can plug into the logarithm. So first, x squared minus 1 is equal to 0 if and only if I factor that left-hand side, that's x minus 1 times x plus 1 equals 0. And the two numbers that solve that equation, the two numbers that will make my denominator 0, are x equals negative 1 and x equals positive 1. So neither of these can be in my domain. Regardless of what's going on with the logarithm, if you plug negative 1 or positive 1 into this function, the downstairs, this fraction will be 0, and that's not okay. That's kind of my first bullet point here. The other thing, I need to make sure that 9 minus x squared is strictly greater than 0. And this is a polynomial inequality. So the way we solve this is also by factoring. I write this as 3 minus x times 3 plus x is greater than 0. But because this is an inequality, I need to find the cut points and plot them on a number line. So those cut points are negative 3 from the second factor and positive 3 from the first factor. That chops up the real line into 3 regions. And I need to determine the sign of this polynomial in each of those regions. You could use end behavior and multiplicities if you wanted. 9 minus x squared, that's a parabola opening down. So in the outermost regions, he will be negative, and inside here, he will be positive. Or you could test a number, right? Like if I test x equals 0, then I get 9 minus 0 squared, which is 9, which is positive. So we're positive in here. And if you test something like -5 over here or +5 over here, you get 9 minus 25, which is -16. So we're negative here and we're negative here. Or you could use the multiplicity trick. These are both multiplicity 1 factors. So you got to change sign as you jump over those. So from here, I can say the solution to the inequality (9 minus x squared is greater than 0) is the interval from -3 to 3, open interval, -3 to 3, right? The endpoints make that equal to 0. I want strictly greater than 0. So I figured out what comes from each of these domain red flags. From the second domain red flag, I know the largest my domain could be is the open interval from -3 to 3. From the first domain red flag, I know that neither -1 nor +1 can be in my domain. So to finish this up, the domain of f of x is, and I'll write it in words first, all numbers in the interval -3 to 3, except -1 and +1. But this is not a nice way to write the domain. I would like to write this set, all numbers in the interval -3 to 3, except -1 and +1, in interval notation. And I think the easiest way to do that, if you're unsure, is to sketch it. So I'll say -3 is here, +3 is here, -1 is here, and +1 is here. The open interval from -3 to 3 is all the stuff between these parentheses. So everything from -3 up to -1 is okay, but -1 itself has got to go. So I chop him out. Everything between -1 and 1 is okay, but +1 got to go. And then everything between +1 and 3 is okay. This set over here is the open interval from -3 to -1. This set right here is the open interval from -1 to +1. And this set right here is the open interval from +1 to +3. This is not -3 to -2. There's lots of stuff between -2 and -1 that I want to include. I just need to chop the single number -1 out. And same thing here, like this set is not 2 to 3. There's lots of stuff between 1 and 2 that I want to keep. So this would be -3 to -1, unioned with -1 to +1, unioned with +1 to +3. This is my domain. So we take all the stuff that keeps the inside of the log positive, that's -3 to 3, and we found that by solving this inequality. And then we kick out anything that makes the bottom 0. So we had to kick out -1 and +1. And that gives us this set, which can be written this way in interval notation. Not too bad, right? This is about as rough a problem I could put on the test regarding domains. Yeah, of course, happy to do it. We do have a few minutes left. Is there anything else you guys would like to play with? I'll bring this list back real quick. So here for a second, in case anybody's still writing. Once again, here's our list of topics. Is there anything else here that you guys would like to take a closer look at before we wrap up our review? Just another domain? Sure. Yeah, let's keep the log stuff involved, but maybe this time we'll do some combination of log stuff and square root stuff. Let's say find the domain of f of x equals the how about the square root of x plus 2 times the common log of how about 1 minus x. So again, here I have two domain red flags. One of them coming from the variables under the square root, the other one coming from the variables inside the log. So from the variables under the square root, I know I'm going to need x plus 2 to be greater than or equal to 0. All right, those are the rules for even roots. The inside has to be greater than or equal to 0. And from the variables inside the log, I know I need 1 minus x to be strictly greater than 0. So what I'm going to do is check and see what's required to satisfy each of these conditions on their own. And then I will intersect those two sets. I will take the stuff that makes this happy and makes this happy at the same time. So first I need to solve the inequality x plus 2 is greater than or equal to 0. And this is a linear inequality, so we can solve this guy just by subtracting the 2. This says x is greater than or equal to -2. So here's -2 on my number line. All the numbers greater than or equal to -2. That's this stuff. The second inequality I have there, 1 minus x is strictly greater than 0. This can also be solved straight up, linear inequality. A few ways to do this. I think what most people do is probably subtract the 1 over. So you get -x is greater than -1. What do I do from here?
Divide the negative on both sides.
Good. So I'll get an x on the left and a 1 on the right. Does anything else happen? What goes in between these?
It becomes less than.
Yeah, this is a less than. So remember, when you multiply or divide through an inequality by a negative, the sense of the inequality flips over. So this, if I try to draw a number line in similar space, I put 1 right here. This says all the x's which are strictly less than 1. So that would be like a parentheses. And then all the stuff to the left of that. And remember what I need both of these things to be true at the same time. So what I'm going to do is take all of the x's in this set and overlap that with all the x's in this set. The stuff that is in both, that will be my domain. So I can say, therefore, the domain of f of x is the overlap. I remember the math word for this is intersection of these two sets. And we can sketch them both on a single number line. It's never a bad idea. Put -2 here and +1 here. So if I take everything from that first set, that's all this stuff. And everything from the other set, that's all this stuff. So I'm looking just for the overlap, which is this stuff. These are all the numbers that are bigger than or equal to -2 and strictly less than +1. And that's it. This is my domain. Okay, so I'm going to go ahead and wrap it up here. Finding domains is definitely going to be a thing on this test. Solving exponential and logarithmic equations is definitely going to be a thing on this test. The other things that you really need to make sure you practice, of course, the other things from this list. Make sure that you're comfortable with the definition, graph, domain, and range of exponential functions, and that you're comfortable transforming those graphs using the transformation rules. Make sure that you're comfortable with the graph, domain, range, transformations of the basic logarithm functions, and also make sure you're comfortable evaluating logarithms, like calculating the base 4 log of 1/16 or something like that by hand. Make sure you're comfortable expanding and combining log statements. That's a big thing. We've seen lots of that in the homework. And make sure you know what the number e is. Make sure you know what the graph of e to the x looks like. And make sure you can transform those graphs the same way you transform the other exponential graphs. That's about it. This test is fairly straightforward. It's just a few sections, and it's all to do with the same sort of topics. So as long as you practice these homework problems and you feel comfy with the quiz problems, you'll be in good shape. If you do want to talk to me about anything, remember you can come by my office hours. I do have an office hour tomorrow from 1 to 2 p.m. You can also Canvas message me, send me stuff on Discord, email, all of that good stuff. Am I forgetting anything? That's it. Test is Thursday. If you're going to take the test at the testing center, you don't need to make a reservation. Just show up there anytime after 12:30. If you're going to take the test online with me, make sure you've got a stable internet connection. Make sure you can sign into the Zoom meeting from your phone. Yeah, that's about it, gang. So I'm going to go ahead and sign off here. Hope you guys have a lovely rest of your day. If there's anything else I can do to help you, don't hesitate to reach out. Make sure you're well practiced on this stuff. This is probably, of all of our tests, the easiest in the sense that it covers the least material. So there's a good opportunity to win back some points. If you haven't done that Jello transformation worksheet, please do that as soon as you can. That is stuff that I need from you. Yeah, that's it. So take care, gang. And like I said, if you need anything, don't be shy about reaching out.